Hello and welcome. In this video, we'll be discussing how we can compare the means from two populations where we don't assume that we know the population standard deviation / variance. So let's jump on in. As we've discussed before, the assumption that we know the population standard deviation, which is an additional piece of information given to us in addition to our data, is usually incorrect. It's pretty tough to meet. Thinking about this, it's very rare that a client or colleague or supervisor will hand you a data set and then say, oh yeah, just so you know, the population variance is 5. That's not how this works. Usually what they'll do, if they ask you to do anything at all, will be to hand you a data set and ask you to find some insights from that data set. Incidentally, if that ever happens to you, confidence intervals are one of my favorite things ever for that kind of open-ended stuff. In any case, they'll expect you to find all of this from data. They're going to expect you to use a method that doesn't really require anything else of them. And those methods exist. So we're going to talk about one. Again, the 3 components, we're going to keep coming back to that: point estimate, critical value, standard error. But what's cool about this is, especially because this is also a test of 2 means and comparing them, this is going to feel very similar to the test that we just did. There's only going to be one change, really. Well, 2 changes. The point estimate looks exactly the same. The standard error is a little bit different. The variances, the S squareds, are now S squareds instead of sigma squareds. That implies that we're going to have to calculate the sample variance from data as opposed to assuming it or being told it. And the critical value is going to be different. We're now going to be discussing T values from the T distribution as opposed to Z values from the Z distribution. Don't forget, T now requires a degrees of freedom. T always requires a degrees of freedom, but now that we're using T, we will need to know the degrees of freedom. And I'll mention when we get to that degrees of freedom piece, i.e. right now, there's just not a nice way to say it. The degrees of freedom for 2 sample comparisons when we don't know the population standard deviation sucks. This is really not fun. The 1 sample case was just N-1. And that was really, really, really nice and easy. This is super yucky. The common way to do this is called the Satterthwaite approximation. And the formula is this nasty, nasty, nasty thing. I will say, you'll note that this is in black. That is, this is pre-filled in your notes. And I do that because I don't want you to get the equation wrong or to miss a square or to miss a parentheses anywhere when you're writing this down. So this formula is kind of a pain, and it's a real barrier to performing these tests. Let me add, though, that if you follow along with our R lecture videos, we're going to be covering how to do this in R. And when we cover how to do this in R, you'll see that once we get it correct one time, you can just copy and paste it, because R is on a computer. You can copy and paste. You can just copy and paste it and then do it again and again and again for any problems that you need to do this for. So the big trick is going to be getting it right the first time so that we can copy and paste that. And we'll do that together. So it's going to be doable, even though it looks very fancy and yucky. We just have to survive it once, and we'll survive it together in that R video when we write all this out. But that's the Satterthwaite approximation, and it is a yucky one for sure. In any case, it's worth mentioning and maybe jotting down the Satterthwaite approximation. This is for finding degrees of freedom. So we're finding the degrees of freedom in a 2-sample comparison of means when we don't know the population standard deviation. That's the context in which we're doing that. And remember, if you recently watched the previous video, in the previous video, we didn't have to do this. So if we assume we know the population standard deviations, we use the Z distribution and don't need a degrees of freedom. It's only with the T distribution where we need to calculate the degrees of freedom. That is in the context where the population standard deviation is unknown. It's only now that we need to use this Satterthwaite approximation. As before, the test statistic looks very, very, very similar. Again, if you use TS, that's fine. Or T, again, we followed the distribution name when we're using the test statistic. As before with our z-test, this equation is with PE equal to 0, but here's the other form of that with PE not equal to 0, and then you just plug in your number, the assumed difference between the two population means. That's what PE0 is, that null hypothesized difference between the population means. All right, so let's look at this airline flights data again. One of the things I'll notice when we're looking at this airline flights data again, one of the different things is that in this new situation, remember in the previous problem, there was a little line in there that in classroom logic, like it's just such a super small throwaway line, but in reality, in the real world, in a real world context, it is a massive line. And that little line was assume the population variance is blank. So again, that little throwaway line in the previous example made the previous example actually quite unrealistic, but that doesn't exist here. And let me just say, personally and professionally, this example is very realistic. So what we're looking at right now, where we collected a little bit of data on two contexts and we want to compare, and we're just going to compare from the data, not assuming anything else, this is a very realistic sample and use case of applied statistics and some of the stuff we're looking at in class. So the t-test, at least in my professional perspective, is a much more utilitarian thing. And so I prefer this section to the previous section because it's just a lot more useful. We just never assume that we know the population standard deviation. All right, so in this test, alpha equals 0.05, going to do the test. So I'll start with the hypotheses, all the same as before with our z-test. The default is 0, and then the alternative is not equal to 0. Again, these are the same as with our z-test. Looking at the test statistic formula, again, PE sub 0 is 0 in this case. That null hypothesized difference value is 0. The null hypothesized value is 0. So I have a minus 0 up top, and I don't even have to write that. That's invisible. All right, just equals that quantity up at the top there. And so this is my test statistic. Again, I'm using T instead of Z. So in classroom logic, you know this because we're in that section. But how do you know this in like a homework problem or a test problem? Well, in the problem, I was not told the population standard deviation or variance. So I have a mean comparison that I want to run. It's between two groups. So that lets me know I'm in this lecture set and in the mean comparison ones. But in that, I wasn't told the population standard deviation. So weirdly, this one that we're covering at second is actually the default, the sigma being unknown. That's the default setting. So if you're not told any other information, you're using this one. And if you're told the additional piece of information of what the population variances or standard deviations are, you can use the other one. But if you're not told that, you use this one. And so that's why we fall into this equation, this formula for the test statistic. So as before, I'll do airline A for group 1 and airline U for group 2. Again, I kind of like writing out our general test statistic PE over SE. That's great, but plugging in the problem specific PE and SE to get the test statistic shown on the screen right now, that's kind of handy because then I can figure out what I need. So I need X1 bar, X2 bar, S1 squared, S2 squared, and N1 and N2. Or I can use, you know, if airline A is group 1, I'll just plug in A's for all the 1s and U's for all the 2s. So I can keep track of airline A and airline U. And so now I just plug all that in, and that's kind of it. I just write out, again, and for me, I have my equation on my paper, and then I have X1, X2, X3, X4, or excuse me, the blanks, X1 bar, X2 bar, S1 squared, S2 squared, and I just go down and fill in the blanks. So that's kind of what we're doing on this slide. And I calculated, the sample means from the data. And now I have the sample variance, and I'm also calculating this from data. So these variance ones in the previous problem, when we assumed we knew it, came assumed from the problem. But now in this approach, we're calculating it from raw data. Again, much, much more useful, less assumptions, more realistic. And now I'm just going to assume that we're finding the sample size from data. The cool part about all this that I want you to see is now we are calculating all of the pieces of the problem from data we're given. And this is where we take a huge step into utility. And t-tests, as we talk about them in our stats classes, they just are a big step for students to take into being useful. Like this is actually a useful method because I can just give you two data sets and say, yeah, run a test comparing them or calculate a confidence interval. And you can do that just using this. So the fact that we can do everything from data, we don't have to assume anything from the problem anymore. That's just such a huge step. And I get in the problem, it's just such a little caveat, a little throwaway line in the problem. But in practice, it is so useful and important. All right, so we still need the critical value from the t-distribution, but remember, to calculate a critical value from the t-distribution, I have to know the degrees of freedom, and so I have to do that Satterweight approximation. So in this case, I use 4 of the pieces of information. So for the Satterweight approximation, if I look on this slide, I use the bottom 4 pieces of information. So I need the same information for the standard error. So on this slide, the top 2 are for the point estimate, the bottom 4 are for the standard error. I need the same information for the standard error as I do to calculate the Satterweight approximation. So that's these 4 fill in the blanks. So if you already have those 4 written out, you can go on and plug those in. I end up with the degrees of freedom of 11.8013. And so this is kind of cool. If you're using tables, you can't find the t-values for fractional degrees of freedom. But if you're doing software, that number exists. Like those exist. You can calculate the integral with the fractional degrees of freedom. So in software, whether it's R, whether it's Excel, whether it's anything, you can put in fractional degrees of freedom and find that. And so that's a new cool thing. So here, the degrees of freedom are fractional. If you were doing this by hand, you would round down, even 11.8. You always round down if doing this by hand and then look in your table. But if you're doing this in software, I just put in to R or whatever, DF equals 11.8013. I just put in that decimal for my degrees of freedom and then ask it to find the cutoffs for this problem. And so for this problem, I end up with plus or minus 2.18 as my cutoffs. Plugging in these new values into my test statistic, I get a different test statistic. What changed? Well, my variances changed. They went from the assumed known variances to these new calculated variances. My critical value has also changed, but I can see that this test statistic is still lower than my lowest critical value. So I've got plus and minus 2.18 as my cutoffs, and this one is lower than the low end one. So this is a significant difference. That is, there's enough evidence to believe that the airlines have a significantly different number of late flights per day. And again, remember, as we lectured on at length in the previous video or two, this is a conclusion about the population. So there's enough evidence to believe this, not just for airline A's week and airline B's week. Again, we can calculate that precisely, but using that information, we feel with a certain degree of confidence, in this case, alpha of 0.05, so 95% confident, that all of the flights for the airline, on average, the average over all of the airline flights are different. That is, there's enough evidence to believe that the airlines themselves, all of the flights, even future flights represented by this sample, are different, have a different number of late flights per day on average. All right, so go on and pause your screen and give this one a shot. Run this using the T test instead of the Z test. Now, I'll note that as you're looking through this problem, you can see that they're giving you not just the, again, this one is a little different because it's not coming from raw data. And if you're working on this by hand, you probably don't want to calculate a raw variance by hand. But in this problem, they're giving you the sample variances. So She found that the mean number of the hours in that group. So she's looking at that sample, calculated the mean, and calculated the variance for that. And again, I'll give you the t-distribution. I'll note quickly, you're missing out on the opportunity to calculate the degrees of freedom here, and that's the Satterwhite approximation. So again, give this one a shot, but realize that degrees of freedom, that Satterwhite approximation, it's something I guess you could do by hand. You don't necessarily have to, but realize that that is missing from this, and that's a big piece to practice potentially. So we're not getting practice on that here. But go on and practice running the t-test. Here's the critical value for you, and see how you do. Pause the video, and we'll come back in a second. All right, coming back to this. I have my null and alternative. The raised group is different. For the raised group is 0 is the default belief. That is, there is no difference. And then we're hypothesizing that there is a difference, that the raised group is bigger, that they work longer. So what formula is needed? Well, we need the T formula. Why? Because we're talking about two samples. We're comparing them. We're comparing their means, their average number of hours worked. And we don't know the population standard deviations. We weren't told that. We were told the variances calculated from each of the samples. Again, a far more common situation. What this situation is a far more common situation than somebody telling us the population variances or standard deviations. And so that's how we know that we're working with this particular test statistic. Again, I'm going to let the raised group be group 1, and then go on and fill in the blanks. So we already had this one from data, the x bar sub r and x bar sub n, or group 1 or group 2, if you did that. But now we have the s squared sub r and s squared sub n. Now, I will admit that for you, this was all just provided in text. So whether the text said calculated the sample variance or calculated the population variance doesn't look that much different from your end. But consider that from the work end, A, sample variance is harder. Like, don't get me wrong, that's an additional calculation you have to do. But B, it's much more realistic because you can always calculate a sample variance from data. And with computers, you'll find it's very, very easy to do. It's not a lot of work to do. But in the assumption end, on assuming you know the population variance, again, that's just very unrealistic. So in this case, though in the problem, again, it looks the same. It's just a little sample variance versus population variance. This actually represents a huge step towards realism. This is much, much more common. This is an actual situation we might see. And again, this was given to you, but you need to know how to find it on your own if you want to be able to find those values. And you kind of need to be able to find those values for this class. All right, so plugging them into our test statistic equation, I end up with 0.3704. Sound right? If not, go double check your work or send me an email if my work is wrong. But comparing this, I get the same result. This is not greater than the critical value. This was a positive test, so I needed to be bigger than the positive critical value, and it's not. There's only a positive critical value in a one-way test. So it needed to be bigger than that critical value, and it's not. So there isn't enough evidence that there's a difference between the groups. That is, I don't have enough evidence to change my null belief, that default belief. That there's no difference. So walked in thinking there's no difference between the groups, and I left. The data didn't really change my mind on that. That's the null hypothesis, and failing to reject the null hypothesis in our hypothesis test. All right, so I mentioned we're not going to do p-values much in lectures, but again, in these first ones and this first lecture set, it's probably worth visiting. So for this example, we've got the computer, and it calculated the p-value for this last problem, this salary one, of 0.714. So that's what our p-value is. So in thinking about the p-value approach, maybe pause for a moment if you don't remember. Go back and check your notes. I want you to put a star or a little flag or a sticky note. And I mean it. Pause this video. I'm going to wait. Pause this video. Go back and check your notes to figure out how we make a decision in hypothesis testing for a p-value. Go, go, go. All right. Did you do it? I hope so. Anyway, coming back, for the p-value, we reject the null hypothesis if p is less than alpha. So our alpha in this case, 0.10, if I remember right. And we fail to reject or retain, stick with that null hypothesis, our default belief, if p is greater than alpha. So for alpha of 0.01, think about, is 0.7 less than 0.10, or is 0.7 greater than 0.10? Hopefully, thinking about it for a moment, we see 0.7 is greater than 0.10. That is, p is greater than alpha. That's that second situation. So we fail to reject the null hypothesis. We're stuck with it. We stick with it. And again, all that means is I went in with a default belief and didn't see anything to change my mind. So we retained this null hypothesis. We fail to reject it. That is to say, there's no statistically significant difference between the raised group and the not raised group. Sometimes you'll see that language. And of course, if you did reject the null, you would say there is a statistically significant difference. But here, we don't have a statistically significant difference. Another way you'll see this is there's not enough evidence to determine a difference. So all these are conclusions. Again, these verbiage for these conclusions work with the critical value approach and the p-value approach. We're just practicing p here because it's worth, again, at the early stages, especially if you've never seen it before, to do a couple of practice runs. All right, so for a different alpha, we might reach a different conclusion. And I mention this because it's worth pointing out that this means that it's not just the data that impact your decision making, it's also your risk tolerance. So if you are allowing a lot more error, then you might reach a different conclusion. But again, you'd be much less confident in that conclusion. So if my alpha were really, really big, say 80, that means the probability of a type 1 error is 80%. Then we might reject the null. Oh, yay, there's a difference. We changed our mind. But like, there's an 80% chance that you're wrong. So like that changing your mind was the wrong idea. That's the type 1 error rate. I changed my mind, but I shouldn't have changed my mind. I should have stuck with what I initially believed. That's the type 1 error rate. And so in this case, it's worth mentioning, again, it's not just data that determine the decisions that we make. In statistical decisions that we make, it's also this type 1 error rate. Of course, in an actual real world situation, it's not just statistics that determine actual decisions that we make, right? So a lot goes into this, but in terms of going into the statistical decision, it's not just data. Even in the statistical decision, it also depends on your risk tolerance. Typical values that you'll see for alpha are 0.05. That's just a very, very, very standard default. Unless you have a really good reason, don't change from that. Sometimes you'll see 0.01, and that's a case where changing my mind and I shouldn't have has a really bad consequence. And then sometimes you'll see this 0.10. I'm really open to change. It doesn't really matter if I changed my mind and was wrong. We're just kind of testing some things out. So the testing phase, are just testing out some new things. Sometimes you'll see alpha of 0.10. Very, very much more common, 0.05. That's kind of the standard. And then 0.01 happens occasionally. All right, so let's jump into confidence intervals. So just like we constructed a hypothesis test, we can easily construct a confidence interval. We just rearrange the pieces. So we've got all the pieces. I mean, these pieces didn't change. I will say for the critical value is the alpha over 2 version, right? So it's the two-tailed version, that critical value. And that's always going to be the case for a confidence interval. So we're going to have to calculate that two-tailed version. You do have to calculate that massive long degrees of freedom to find that t value, right? All t distributions have a degrees of freedom. And it just so happens that the two-sample test of means, with sigma not being known, the degrees of freedom for that test is just kind of a pain. So for this critical value, you still have to do the Satterweight approximation, but all the pieces are the same. Point estimate, standard error, critical value. Critical value is just the two-tailed version. Confidence interval, again, you just plug in their pieces, and all these pieces are the same as we had for the hypothesis test, for the t-test hypothesis test. So everything should feel very, very familiar here. So the airline flights, again, you've seen this. I won't relist the data. I'll just relist all the values that I had to calculate the point estimate and standard error, and I'll relist the critical value. Again, for mine, it was a two-tailed test, so I just get to reuse that same critical value. Plugging in these numbers, I get my interval. I'll notice the interval for a t-test is a little bit wider. This is common, all other things being equal. All other things are never equal because the standard deviations are estimated from data here, and they're assumed in the z-test. So shouldn't say all other things being equal. But if the observed data was exactly had exactly the variance of the assumed population variance, then the t-test would be just a little bit wider than the normal distribution. That's the case here as well, though probably in larger part because of the variances are bigger than we assumed in the z-test. In any case, we've got a wider range. Now, I'll note for both of these, neither includes 0. So the belief that there's no difference between airlines is not reasonable. It doesn't fall in that reasonable range. So reasonable beliefs regarding this based on the data look like that there is a difference, and that the difference is that the Airline U has a higher average late flights per day than Airline A. So that's the difference between these. That's the reasonable range of values here, is for these. And again, the negative sign just indicates Airline A is lower. So when we look at the negative, everything in the reasonable range indicates Airline U has a higher number of late flights per day. Airline A has a lower number of late flights. And again, just worth re-emphasizing, I can't say it enough, this interval is not for those 7 data points. We know exactly how far apart the averages of those 7 data points were from one another. This is for all flights for these two airlines. On average, for all days, the average of Airline A and Airline U has anywhere between 2.5 and 13.5 more late flights per day than Airline A, on average across all flights for the airlines. And we're 95% confident about that. All right, well, now it's your turn. So you'll get to go try this one out. I will note I'm giving you the test statistic again, or the critical value again, the t-value. Note that this changed, and again, consider why. And if you don't remember why, go back and look at the z-test. We talked about that in the z-test video a little bit. But yeah, consider that this is a different critical value. So go and practice this one on your own. And if you have access to a computer, go on and try to find the test statistic. If you've glanced at any of that R stuff. Go on and try to find not test statistic. Go on and try to find the critical value on your own and construct the confidence interval. But otherwise, yeah, give this one a shot on your own. See how you do. Pause the video. We'll touch base in a second. Got my tea here while I wait for you. Or maybe you just came back, and so I'm drinking tea right to start. In any case, let's get going. So, answers. Plugging these values into their appropriate place, we find the 90% confidence interval. And again, this is just the PE plus or minus critical value times standard error. That's all this is with the pieces plugged in. I plug in the numbers for the individual pieces and then hit enter on my calculator. Remember, for this problem, we're comparing raised to not raised groups. So this would suggest the negative sign, meaning the not raised group, worked 2 more hours. The positive sign, meaning the raised group, worked 3 more hours. So it's reasonable to believe anything between the not raised group worked 2 more hours than the raised group. On average, overall, like if we implemented this policy, the average for everybody, not raised group is working more than the raised group by up to 2 hours, or the raised group worked more than the not raised group across everybody overall by 3 more hours. Both of those beliefs and everything in between are reasonable to believe. And so that's why we say there's not a significant difference. We don't have enough evidence to determine one is better than the other here. And again, when we were doing the hypothesis test, we're just going in one direction. So we definitely don't have enough evidence for that. So yeah, this represents the reasonable range for the difference in the average number of hours worked. And again, because 0 is not in here, and 0 was the PE sub 0. 0 was the null hypothesized value. So that's what we look at. We don't just look at 0. We look at the null hypothesized value. So because the null hypothesized value wasn't in the confidence interval, we don't reject it. Again, it's the null hypothesized value is in the confidence interval here. 0 is in the confidence interval. So it's reasonable. The confidence intervals are reasonable range, and your default belief is in the reasonable range. Your default belief is mathematically, statistically reasonable. So we're not going to change that default belief. We're not going to reject that default belief. We're not going to reject that null hypothesis. All right. So again, we've got a couple of APA write-ups here. We'll continue to do these throughout the course, but less and less often. A few more at the beginning here as we get used to this. But the example APA write-up, note that I'm doing standard deviation, not variance. Again, we need variance for the calculations, but standard deviation is more typical to report. Also note that in the previous one, I wrote something in text here in the previous one talking about how the variance was assumed to be X, Y, or Z. And in this case, that's not the case. I'm not making any assumptions about the variance. I'm calculating it. So where I report that's a little bit differently. Previously, I had a little statement that said I assume the variance is going to be 4. Here, instead of that, I have something where I show the calculation for that particular group, and I was showing the mean. Now I just include the standard deviation at that same spot in that same parentheses. You'll also note in this write-up, I mentioned that the Satterthwaite approximation is used to determine the degrees of freedom. There's a couple of different methods, and Satterthwaite's a pretty good one. So I mentioned that and describe how did I get degrees of freedom from a 2-sample test, because that's a question. In any case, a lot of this looks the same. Maybe one more thing that I'll note is if reading through at the alpha equals 0.10 level, not enough evidence, blah, blah, blah. And then again, we see mean and standard deviation. Once we get to the statistical reporting at the end, the p-value and confidence interval look the same, but the t looks a little bit different. So you'll see previously it was z equals blank. That's the test statistic. Here I'm using t because the test statistic's from a t distribution that's common, but I have a parentheses. And what you'll note is that inside the parentheses is the degrees of freedom. So for statistics that have a degrees of freedom, it's typical to report the distribution as your, test statistic, so t, and then parentheses, and then you put your degrees of freedom inside the parentheses, and then you close parentheses equals, and then you write your test statistic. So here, reading that t 16.08 equals 0.37, the 16.08 represents my degrees of freedom, and the 0.37 represents my test statistic. All right, well, in this video, we discussed how we can compare means from 2 groups without assuming we know the population standard deviation / variance. We also talked about how we can do a confidence interval with these. So thanks for sticking with me, and I look forward to seeing you in the next video.